Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's do the Python part for module number 5, machine learning for time series in Python. We're going to do things in Scikit-Learn from scratch, and once we're comfortable with that, we are going to move on to PyCaret. So I have a couple of slides here, so for those of you who have not watched the theory lectures, please make sure that you watch them before moving on to the Python part, because there's lots of things that we have covered, especially we talked about the challenges in doing machine learning using Scikit-Learn in the previous one, and now we're going to see those challenges and address them. All right, and again, as I said, there are a couple of slides here that's going to help you understand the data pre-processing part for a single output setup and a multi-output setup better. So I'm going to open up the Python file now, and then I'll go back and forth between these slides and the Python as we move forward. Okay, let's open the notebook, go to my GitHub account, to deep forecasting, lectures and codes folder, and then module 5, machine learning for time series forecasting. We covered the intuition file last time in video 2, I assume, yeah, part 2, and now we're gonna do the entire thing. Okay, you should be able to run it in Google Colab if you want. If you're doing Google Colab, remember you need to pip install PyCaret, the full version, because at the end of this notebook, we're going to use PyCaret. We start with Scikit-Learn, but we're going to end up with PyCaret. So let me just quickly double check that the link is working. Yeah, it should be good, but I already have it open on my local computer, so I do this one in the VS Code. And then I think when we get to the deep learning section of the course, we are going to switch to Google Colab simply because we need GPUs. All right, so this is it. Let's begin. Again, I'm using my deep forecasting environment, which has already PyCaret installed in it. So let me walk you through the code, and it should be pretty straightforward. And I'm going to highlight the points that I want to emphasize. Okay, importing the packages. We're going to work with our simple airline passenger data set, and then obviously you can apply any time series data set you want. This is a univariate time series, and everything we do here applies to multivariate as well, just be aware. And we're not doing any kind of fancy feature engineering. We're using some simple lag terms, but as I said in the previous theory lecture videos, doing the right feature engineering is a big deal, especially for time series forecasting, especially if you're doing machine learning. So I want you to spend some time learning how to do feature engineering, how to create the different time series based features based on your different tasks, right? Here, I'm going to keep it simple because we want to talk about we want to get the intuition very well. And I assume that, again, there's a lot more going on here. And I assume that you are savvy enough, you can figure it out by using ChatGPT or any other large language models out there. All right. So I'm going to go ahead and, as I said, show you what are we trying to prepare here. So this is our time series data, right? So this is airline passenger. We have observation from number 1 all the way to 144. These are months, right? We're going to split it into train and test. We're going to use 132 of them for train and the last 12 observation for test. And the goal is to make this univariate time series into a supervised data frame for machine learning. And I'm going to start with 2 lags and 1 target variable. So this is at the end of the day what we're going to see. So this is going to be our new train set. This is going to be the new test set. And as you can see, we have a couple of features and 1 single output, which is a target variable, right? So that's the plan. All right. So how do we make supervised machine learning data? So here, as I said, the test period is 12. So the train period is going to be 144 minus the 12. So it's 132. If you run this cell, you'll see 132 observation for train, 12 for test. We can visualize it. And as you can see, again, not surprisingly, the first 130 observations are train, and the orange one is a 12 observation for the test. Okay, so and I'm going to show you the type of the index. Again, as you can see, these are monthly data, and that's the type of the index. And I'm going to go ahead and create a Boolean indicator. So this is for visualization. I want to keep track of the index of the time series, both in the train set and test set. We're going to use these booleans later on for adding the prediction to the right data frame and for visualization. So I say that if the index of the data is less than, again, this is the last observation in the train set, call it train indicator. So basically true, otherwise false. And the test indicator is basically the other way around, right? Any index greater than the last index of the train set. So this should make sense. And if I show you the test indicator, so it should be false for all the 132 observations in the train set and true for the 12 observation in the test set. Again, we're going to need this for visualization and when you're updating the columns in our new data frame with the predictions. We're going to do one step ahead prediction, multi-step ahead prediction, and multi-output prediction. So that's why we need these indices when we do the visualizations. All right, so I'm going to go ahead and create a simple series based on our target variable. So the passengers is going to be our target variable, dropping an A's, and then make it a simple NumPy series. So this is a data set, right? Going from 112 all the way to 432. And the length is going to be 144. So this is the part that we are transforming this univariate time series, which we call it series here, into our supervised machine learning data, right? So there are some notations I want you to be aware, and I'm going to stick to this notation through the rest of this notebook. And also we're going to use the same notation in the deep learning section of the course. So just bear with me. This is pretty straightforward, by the way. So I'm going to use tx as the number of lag variables that we're going to use. Basically, this means that, so let me actually open up this one. We're going to use the past 2 observations to make a prediction for the next one, right? So this can go easily to 12 lags, 20 lags, whatever, right? So here we're going to keep things simple and stick to 2. All right, so this is the, I call it tx, and then we have ty, which is obviously your target variable, the number of outputs we have, right? So here we are talking about the single output. Let me actually bring it up again. So if you have single output, there's going to be only one output. If you have multi-output, there's going to be multiple output, right? So here our ty is going to be equal to 1. Here our ty is going to be equal to 12. So we're going to see because we're going to have 12 outputs in the multi-output thing. All right, so let's go back. This is the ty. And then the goal is to create those observations in the data frame, right? So I'm talking about these observations. Again, we're focusing on the single output, and we want to replicate these observations, y1, y2 features, and y3 output. y2, y3, y4, y3, y4, y5, all the way to y142, 43, and 144, right? So let's do that. So I create a list comprehension. Basically, this is pretty straightforward. I will walk you through very briefly, and then I'll show you how you can get help from LLMs, right? So as you can see, we're going from this T goes all the way to length of series is 144 minus 2 minus 1 plus 1, so all the way go to 142, right? So the index goes from 0 all the way to 142. And then that's your x is going to be, and it's going to, for example, 0 to 0 plus 2. So it will be the index 0 and 1. And the last one is going to be 142 all the way to 144. So not including 44. So this is what we're doing, right? 1, 2, 142, 143. And then obviously for the target variable, there's going to be only one single output. This is pretty much the same, but we are saying start from your observation plus 2. So whatever it is, so we're talking about y144 here. So whatever it is plus 2, because you want to exclude those features, all the way to whatever number output you want to have, in this case 1, right? If this was not quite clear, the best way for you to learn this is you can copy this, right? And then you have multiple resources. You can, if you're using VS Code, you can go ahead and use GitHub Copilot. So this is going to open, and by the way, GitHub Copilot is free. So you can, if you're a student, it's free. I think even if you're not a student, they either reduce the price like crazy or it's completely free. So you need to check it out. And then you can say, hey, for example, explain this cell to me step by step. Okay. step by step, and then you paste it, right? I can copy this prompt. And again, if you're not coding in VS Code, if you're doing in Google Colab have its own generative AI, so you can use that one. And if not, you want to try different, let me see what I have. You want to try different generative AI LLMs. So this is my go-to tools. I typically do Grok, ChatGPT, Claude. Recently, I've been using DeepSeek. This is a Chinese LLM, which is insanely powerful. We don't know how it goes. We'll see. And then Gemini. So basically 1, 2, 3, 4, 5, you have 5 awesome LLMs by your side to help you understand the code. Okay, so there should be no excuse in terms of, okay, this part was complicated. How can I learn it better, right? So this, as you can see, it explained it in very detail to you how you can basically understand this part of code. So that's why going forward, I will not focus that much on the codings. Simply, I assume that you have your best buddy around you, your LLM, and they can teach you how to basically self-study these things. All right. So when we run this, let me see. Actually, I need to rerun. Let me go ahead and rerun the cells above this one, because I guess I reset my environment. Yeah, there you go. Okay, and then you will see. This is going to be our entire new data frame, right? Your feature space has 142 observations with 2 features, and your target variable 142 observations with only 1 column, which is single output, right? So basically we replicated this, right? We haven't divided into train and test yet, so this is our next step. So right now we have all these things in a data frame, and our next step is to split it into train and test, right? Obviously we're gonna use the first 132 observations for the train and the last 12 for the test. Okay, so let's go back. Yeah, it doesn't, I just say that to understand this better, go ahead and try these numbers and etc. etc. Okay, so this is the, let me see. Did we not run this one? Let's see, there you go. Okay, so this is the data frame that we were talking, this is the features, right? And these are the target variables, this is single output. Next step is to go ahead and basically put them in a train and test it, right? So this is pretty straightforward. I just wanted to show you that, for example, what is the shape of your X excluding the test period. So this is the first 130 observations, and your test period is 12 observations, right? So this is what we have here. So this is going to be 130 observations here, and then the last 12 observations are your test set. And then we're gonna put it in this cell, X train, Y train, X test, Y test. So hopefully this logic should make sense now. And we're gonna apply the same logic to both X and Y to get the X train and Y train, and X test and Y test. Okay, so this, as you can see, this should be pretty straightforward, right? This is our X train, Y train, X test, Y test. All right. With that, now we have a data frame which is pre-processed from a univariate time series to a supervised machine learning data set. Now we can simply apply any kind of Scikit-Learn machine learning model to that, right? Just for the sake of presentation, I'm going to work with decision tree regressor, random forest regressor, and then for the metrics, we're going to use mean absolute percentage error. So MAPE, or mean absolute percentage error, this is not the best metric out there, especially for time series. It can be biased, it can be exaggerated if there are some small numbers. But for this example, when you're using airline passengers, that's fine. We don't get for example, a small tiny denominator, and then this cannot artificially get exploded, right? So we can trust that one. A better metric can be root mean squared error but again, here I want to keep it interpretable, so I'm going to use mean absolute percentage error. Yeah, our first model, let's go ahead and train a simple decision tree. So this is the model, we're going to fit and train it. And now we have a model. Now, with that model, we can go ahead and do one step ahead prediction, and then later on multi-step ahead predictions. Okay, starting with one step ahead forecast, right? Remember, at each point in time, we have access to the past TX lags actual observations. So again, if you're in here, observation number 3, we have access to the past 2 lags, and we want to make a prediction for the next one. If you're here, 130, 131, we want a prediction for 132. Okay, so that's what we are saying here. And obviously, the first 2 observations, Y1 and Y2, we cannot predict them. So I'm going to go back and then switch them into false. Let me tell you what I mean. Look at that. The train indicator, which we created a Boolean for later visualizations, I'm going to say, go ahead and replace the first two observations to be, instead of true, to be false, because those TX values are not predictable, right? If I'm using 10 lags, I cannot predict the first 10 observations. If I'm using 2 lags like here, I will not be able to predict the first 2 observations, right? So we're going to switch them to false. Now, if you look at the train indicator, the first 2 is going to be false. Then the next 130-ish is going to be true. And then the last 12 is going to be false, because this is your test indicator. Okay. So our test indicator, as I said, it's going to be all of them false except the last 12. So as you can see, later on, we're going to use these Boolean indicators to add the predictions to the data frame, and we're going to use them for visualizations. All right. So let's go ahead and make some predictions, both in the train set and the test set. So simply we can go ahead and use from Scikit-Learn, we can use the train model.predict, and you pass the data set, right? If I do the decision tree model.predict xtrain, it's going to give me the decision tree 1 step ahead forecast in the train set. So this is the way we are naming them. And if I go ahead and say predict xtest, it's going to give me 1 step ahead forecast in the test set. So this is very important, guys. This means that if you use any Scikit-Learn models for your time series forecasting task, and if you simply go ahead and train it and do .predict, at best it will give you 1 step ahead forecast, and that's it. So if you want to do multi-step ahead, you have to do something else. It doesn't come, so there is no module in Scikit-Learn that automatically does it for you. If you want to do multi-output, again, the same story. You cannot simply do .predict. You have to put it in a for loop and you create it yourself, right? So that's why I want you to be very careful that do not blindly apply any machine learning model from Scikit-Learn to your test set or your train set and think that, okay, you have multi-step ahead prediction, you have multi-output prediction. What you get from that .predict thing is 1 step ahead prediction. So that's why it's fundamentally different how we apply Scikit-Learn models to a time series task. Okay, so as you can see, we're going to have 130 predictions in the train set and 12 predictions in the test set. So these are basically a bunch of numbers, right? So for example, I can show it to you, but this should be pretty straightforward, right? So there are going to be 12 numbers that are predicted. And I'm going to add those 12 numbers to the prediction in the test set and those 130 numbers to the prediction in the train set, right? So this is our original data. If you remember, I can show you the original data as well. So let's do data.head. So this is original data, right? And we are going to add the prediction in the train set to the first 132 observations, excluding the first 2, remember, because you're not predictable. And then we're adding the last 12 predictions to the tail of the data set, right? So this is where the train indicator and test indicators are becoming handy. Okay, so look at that. In the train set, we cannot make a prediction for the first 2 observations, but the rest has predictions. And obviously, if I look at the tail of the data, these are the predictions for the test set, right? So if I do tail 13, it should make more sense, right? So the last 12 observations are predictions in the test set, but obviously the one before that, it's in the train set. Okay, now with that, I can simply visualize it. I can use data and then pass the name of the columns. We have passengers, 1 step ahead forecast in the train set, 1 step ahead forecast in the test set, yeah, and then we can label it. So these are the predictions, right? So again, the blue line is the airline passenger data. The orange one is, as you can see, in the train set. So the first 2 observations are not predictable. The model is doing an awesome job. A simple decision tree is doing an awesome job in the train set, but in the test set, it's having a hard time. So this was the 1 step ahead forecast. Next, let's look into the multi-step ahead forecast. For multi-step ahead forecast, remember, this is what we're going to do, right? So we don't have access to this blue line anymore in the test set. We don't see the test set. We're going to use the previous observations, how many lag terms, whatever it is. In this case, it's 2, to make a prediction one step ahead. And then we're going to use that prediction and the previous observation to make a prediction one step ahead, right? So that's why when we're doing multi-step ahead forecast, we cannot simply go ahead and do model.fit x test. If I do model.fit x test, it's going to give me this green line. It assumes that at every single point in the test set, we have access to the blue observations, right? But for multi-step ahead forecast, we don't have that luxury. So let me actually try to show it to you here on the slide. So let's say you want to forecast into the future, right? So here I have observation 142, 43, and make a prediction for 44, right? So, and then let's say, again, this is your test set, right? You have this observation. I said that I'm going to use the past 2 lags, 143, 144, to make a prediction for the next one, 145. Then, if I want to forecast into the future, again, multi-step ahead, I use 144, this is blue, I have it. Then 145, which is a prediction, I use these 2 numbers to make for 146. Then, from step 3 onward, it's all the forecast is based on previous predictions, right? 145 itself was a prediction. 146 was a prediction. So I'm going to use those 2 predictions to make another one 3 steps ahead, right? So we're going to do this thing in the test set as well, right? So for example, in the test set, I will start with this 131 and 32, which is, remember, these are the last observation in the train set, and make a prediction here. And then I'm not going to use the actual numbers anymore. So I will be using those predictions along how many lags previously it was available, right? Hopefully it makes sense, but the whole point is that you cannot simply do model.fit x test and expect to get a multi-step ahead forecast. And what is the process? You have to put it in a for loop, right? So you need to grab those last 2 observations, make a prediction for next, and then add that prediction to the previous observation, make a prediction for next, and etc., etc. So we're going to create that for loop here together, right? In order to show it to you, I added a bunch of cells here to make sure that everybody is on the same page in terms of numbers, right? So let me show you the X test, right? So this is our test set, features in the test set. So this is what we have. The shape is 12 by 2, right? So we have 12 observations in the test set, and each of them has 2 columns, right? Then I'm going to grab I want to show you the shape of the first observation in the test set. Right now it's an array, right? I'm going to reshape it into a row vector by doing reshape 1 and -1. So now I have a row. So what I'm trying to do here is that I need to pass this thing to model.fit, right? So what we're doing is something like this. Remember, guys, look at that. I'm taking these 2 observations, 131 and 132, make it row vector, and then pass it to model fit, and model fit is going to give me this. Then I need to roll this thing over. I think if you follow it beyond the X test, it makes more sense. Well, at least visually, it's easier to see it here on the slides, right? So I'm using these 2 to make a prediction here, and then I need to roll this over to the left, right? I need to roll 144 to the left, and then roll this one to the left. So we're going to use this concept of rolling in the next cells in a second, okay? So now hopefully you know why we are reshaping these things to a row vector, because we need to pass it to the model.fit, and that's it, right? So where are the observations here? I'm going to show you the tail of the train set. Look at that. The tail of your train set is this. Look at the past 2 observations, 362 and 405, right? So this is the tail of your train set. The observation number 131 and 132, right? We're gonna, and if I look at the first observation, the very first observation in the X test, it should be something like this. Take these 2 numbers, 131, 132, 131, 132, make a prediction for 133. This is exactly what we're doing. So look at again, this is the tail of the train set, 362 and 405, the last 2 observations. Our test set, the first observation in the test set is the same thing, 362, 405. Now you can see that we're going to use, of course, I need to reshape it to a row vector and then pass it to model fit. Or by model fit, I mean model.predict. Sorry, if I said model fit, I was misspoken. So I mean model.predict, because you want to predict something, right? So yeah, so this is going to be my new input X. I want to call it, let's say, again, we're going to put it in a nice cell, but I try to break down that cell for you before we jump ahead, and then hopefully avoid any confusion there, right? So this is going to be the input of my features that I'm going to add to predict. I need to change it to a row vector and then make a prediction. Give me the first element of that prediction, right? So if I do that, what is happening behind the scene? It is using 362 and 405 and pass it to the model that has been trained, and that model is expecting a feature with 2 columns or X with 2 features, and that's what we're doing, and it's going to give you a prediction. So the prediction is going to be 396. Now if I go ahead and show you the head of the test set, so this is actually for January, this is January 1960. The actual was 417 and we predicted 396. Do you see that? We are using November, December 59 to make a prediction for January 60, right? So this is the actual, this is prediction. And now when I want to forecast into the future, instead of using this number, I'm going to use the prediction. I'm going to use this one and this one to make a prediction for this one. Hopefully it makes sense, right? So let's go. How do I do that? I'm using this roll function from NumPy. I say roll whatever vector you have by 1. So basically it's going to take this one, this vector, where was it? This vector, and roll it by 1. So the 405, it's going to become here, right? And then there's a space for this element. I'm going to replace this element with the prediction. So this is what we're doing, right? So roll that one by 1 and then input the last element of this new input X by prediction and then print the prediction. Well, print the new input X, right? So as you can see, now we used to have 362 and 405. Now we should have 405 and this, 396. This is exactly what we get. And we're going to repeat this, right? We're going to put this 396 here and then make the new prediction here. So this is going to be your new input X. So I'm going to put it in a nice cell and hopefully you can interpret this cell a lot easier now, right? So we're going to create a placeholder for our multi-step predictions. So it's an empty list. And then your input X, the first element of your X features for in the test set is this one. So basically we're looking at this one, this row, right? We make a prediction for this and then rolling it using the next future for predictions, right? So that's it. This is the first one. And we say while the length of your multi-step ahead predictions, whatever it is less than your test period, in this case 12, keep doing that, right? What is keep doing that? No, make a new prediction. Use model.predict, input reshape, again, make it a vector, a row vector, and then add that prediction to your multi-step ahead prediction. Do you see that? So this is going to be your prediction number 1, and then roll it over. So your new input X is going to be your old one, roll it over, and then replace the last one with the prediction. So keep doing that until you have predicted, in this case, 12 observations, right? So here, in this case, we have 12, the test period is 12, but we can go beyond that, right? If I change that test period, well, you can replace this test period either with 12, or if you want to predict into the future as well as the test set, you can make it 24, 36, you name it. You can do whatever you want, right? But in this case, we're going to go all the way up to the 12 because we want to have the luxury of having access to the actual observations in the test set. We have predictions in the test set. We can go ahead and calculate the MAPE or the RMSE or whatever other metrics, right? Obviously, I can predict into the future as well, but if I do that, then I cannot compare it with anything, right? We cannot come up with a performance metric. So that's why in the test set, we're gonna make predictions multiple step ahead all the way to the last observation in the test set. So that's why we can report some metrics. All right, so these are the multi-step ahead predictions. Well, let me actually run this line. There you go. So the first one, we already did that. It was 396. The next one is 420. The next one is 472. And now we need to compare these ones with actuals. What are the actuals? The actuals are the blue lines here. So these are the actuals. So we can go ahead and add it to the data frame, plot it, and do all the cool stuff, right? So let's go ahead and do that. So I'm gonna go ahead and add this multi-step ahead predictions in the test set, right? And we can look at the tail of the data, right? So one step ahead was this, multi-step ahead is this. So hopefully you get the difference between the two, right? So one step ahead forecast, for example, this one is using the actual values of, let's say, August and September, and then make a prediction for October. However, this one is not using the actual values, right? It's using the previous values. So for example, it's June and July, and make a prediction for August, and use August and let's say July, make a prediction for September, and then use August and September, make a prediction for October. So this is why they're different, and you should now understand why they're fundamentally different, right? So let's go ahead and create this data frame, and we can visualize it, right? So this is the difference, right? For example, the blue one is actual in the test set. The orange one is going to be one step ahead forecast in the test set, and the green one is going to be multiple step ahead forecast in the test set. And because we go all the way to the last observation in the test set, we can go ahead and report the performance metrics. This is something that I'm going to go ahead later, but before that, let's talk about multi-output forecast. For the multi-output forecast, the only change we need to make in terms of data preparation is changing the TY to test period, for example, 12, right? This is the number of outputs forecasted at once. So let me show you how it looks like. So this is our single output. Now we move from single output to multi-output, right? So again, here the testing horizon is 12. The idea is that we're going to use every information we have, and then we passed the two features, and we're going to predict all the 12 observations at once, right? So let me help you with the indices here. So remember, our train set goes from Y1 to Y132. So what we need at the end of the day is Y131 and Y132 as our lag features to make a prediction for all the 12 observations here. And this is what we have. You see, Y131, Y132. This is one row of observations, and we're going to take those two numbers and make a prediction for the next 12 days, right? And obviously it's not going to do a good job because we're only using two lags, we have only one observations, and etc., etc. But the model has been trained on all the previous observations, right? So we have 130 observations, the model has been trained already, taking these things and then make a prediction all at once. So the way that model is being trained is that now we have to be careful about the X train, X test, Y train, Y test, right? The X train is pretty much the same, but the Y train is different now. So each Y train has a shape of 130 and 12, right? So because, and then once the model is being trained, at each observation, it's going to take two numbers and make a prediction for the next 12. Take two number, make a prediction for the next 12. And obviously, if you want to forecast into the future, we are going to take the last two observations in the test set, 143, 144, and make a prediction all the way to 156. Use to 12, make a prediction for the next 12 observation. All right, hopefully it makes sense. Now let's go ahead and create these data sets and then simply use a model.predict and pass the data set, and it should do the job for us. Okay, so again, this part of the code does not, this is pretty much the same. We only change the TY. And now if you look at the shape, we have, again, for X, and this is the entire X. So I haven't split it into train or test yet. This is the entire new supervised data frame, 131 and 2, 131 and 12. So this is what we're talking about, this one. 131 and 2, so this is the X. And this is, I can use my drawer too. So this is the X. The shape of the X is 132 by 2, and this is the shape of the Y, which is multi-output now, 132, by, let's say, 12. It's 131, sorry, let me see that. Yeah, 131 by 12. Okay, cool. And then exactly the way that we did for multi-step ahead forecast, I want to walk you through some cells to just give you a sense that why this train set and test set, where is it coming from, right? So let me actually show it to you. So look at that. I'm showing the first 14 observations in our time series. So basically, just for the sake of presentation, I'm showing the first 14. So this goes all the way to Y14, okay? And then what do we do? So what is the first row in our X and Y? So let me show it to you. And then the X, the first row in X is gonna be 112 and 118. And then the first row in your target variable is going to be 132 all the way to 126. You see, 132 all the way to 126. And we're going to go down the data set just using these basically numbers, right? So we already show that here. So this is exactly what we're doing, right? And now I want to show you the shape of the very last row of your X. So the shape of the very last row of the X is 130 by 2, right? So again, there are going to be 130 observations with 2. So I'm talking about this one. So we want to think of it as X train. This one, maybe I should have used another color, as Y train. And then this is X test. And this is going to be our Y test. Okay, so that's what we're doing, right? All the elements in X, excluding the last row, is your X train. The same story for Y train. And the last row itself in the X is going to be your X test. The last row in the Y is going to be your Y test. Okay, so I'm going to call it Y train underscore MO stands for multi-output, and then X test underscore MO for multi-output. Okay, cool. Now we have our supervised data set. So we can check out the shape as well. So this should make sense, right? All right. So just look at that. Your Y's have 12 outputs. Okay. And in the test set, there's only one row with 12 outputs. Okay. So now we can go ahead and create this multi-output predictions in the train set and multi-output prediction in the test set. And as you can see, we're going to fit the data using the train set and make a prediction in the test set. We don't need to put it in a for loop anymore, right? Because we are not using previous predictions, for example, the way that we did for multi-output. We're not using previous predictions to make a new prediction. So we are using everything we have. Let me actually erase it. So we are using everything we have in the actual data, which is this, to make a prediction multi-output. So if your machine learning models allow this kind of output, like decision trees, like random forest, all these decision tree based models, or if you have a neural network with 12 nodes at the end of it, then you're going to get all these things at the same time. So when I train a model with this data set, with this kind of shape for the output, if I do simply .predict, it works both in the train set and test set, because again, it's going to predict all those outputs, in this case 12, at the same time. So I don't need to put it in a for loop. So hopefully it makes sense. And now, as you can see, the shape of the predictions in the test set is 1 by 12. So basically 12 numbers. I can look at those numbers. So 465, 467, and etc. And then we can add those multi-output forecasts in the test sets in the data set. Okay. So once we have that, the reason that this thing is getting updated because I reran the code, and every single time there's a random initializations in the decision tree model. Okay, then we can plot this. Okay, so this is how it's going to look like, right? So now we have everything. We have the actual data in blue. We have one step ahead prediction in orange. We have multiple step ahead forecasts or predictions in green, and we have multi-output forecasts in red. And obviously the red one is the worst case here, simply because we are literally only using 2 observations here to make these predictions for the next 12, right? And again, I understand the model has been trained using the train data, but using 2 lags to make a prediction for 12 forecasting points into the future, it's not going to work as expected, and this is not surprising at all. All right, so again, we can go ahead and simply run a comparison between the 3 models. I'm going to use MAPE. I explained why MAPE is a good one here, but be very careful. Again, in time series, MAPE is the tricky one. You have to make sure that your MAPE is not biased. In this case, because the starting point is 100, so we're not going to have it exploded MAPE, mean absolute percentage error. So we can, what I'm doing here is simply, these are our actual Y's. the blue line, and I'm simply compare them with different observations from different predictions from different models, and simply calculate the mean absolute percentage error. So yeah, for the one step ahead, 10%. So these numbers speak to what you see here. So for the one step ahead, 10%, for multi-step ahead, 16%, for multi-output, 23%. So these are the errors, right? Mean absolute percentage error. And this is typically the case. Obviously, your one step ahead is going to be the most accurate, simply because it's using all the information until the very last day. Multi-step is going to be next best, multi-output is going to be the worst. And again, this is typically the case. For deep learning, sometimes the multi-output is better than multi-step, but for machine learning model decision tree based, this is typically what you're going to see, okay? And hopefully, again, I really want you to understand what is the difference when it comes to training and making forecasts into the future using either of these models. Okay, now, this cell, we're going to put everything in one nice function. Again, you have seen everything inside this function before. So this is me putting everything in the previous cell in one cell and make a function out of it. And I want to make this function as close as possible to PyCaret's function. Because guys, remember, as I promised to you, we are going to replicate a PyCaret function for time series, right? So this is me showing you how you can use Scikit-Learn and basically replicate what PyCaret is doing for you. So I have a function, it's expecting a data, it's expecting you pass a target variable. So this is more flexible than a PyCaret. You can specify how many lags you want to include in the features. So for PyCaret, you don't have that option. I think by default is 10. And this is forecasting horizon. What model you want to use? So these are going to be any Scikit-Learn package compatible model. And this is a model name, so you can name it whatever. So this is going to be a string, right? And as I said, you can use any machine learning model, right? You can do, for example, decision tree, random forest, linear regression. And we're going to compare them. And inside this function, I'm going to do only one step ahead and multi-step ahead. I'm not going to do multi-output. So that's why we can use linear regression. If you want to do multi-output, you cannot use linear regression, okay? And this is what PyCaret does. PyCaret will not generate multi-output forecasts for you. So if you're curious to how you can do multi-output forecasts using PyCaret, the answer is you cannot. Well, there's a workaround, but it's not worth it because PyCaret function is heavy itself, and if you put it in the multiple for loops, so it's not going to be efficient. You will be better off doing your multi-output results using a method that I did here. Just prepare the data and pass it to a simple model.fit and model.predict. Okay, so again, you can pause the video and go through this cell all by yourself, but this is pretty straightforward. There's nothing new here. Everything we did in the previous cells, I put it in one nice function, and I add some visualization to that, and I report some metrics, right? So let's go ahead and run this function. Now I call it my ML time series forecaster, and then now you have a machine learning time series forecaster that if you pass any Scikit-Learn package model, it's going to do the job for you, okay? So here, again, this is a new cell. We are importing a new data frame. The data frame is your airline passenger monthly data. You pass the data frame, you pass the name of the target variable. If you have worked with PyCaret, you know that this is the way that we pass the inputs to the PyCaret function, right? Now we can say use 12 lags, forecasting horizon 12. What model do you want to use? Again, decision tree regressor here. It can be K nearest neighbors regressor. It can be SVM or SVR. It can be any Scikit-Learn compatible model. And model name, you can specify whatever string you want. You run it. So when you run it, it's going to train the model. It show you the mean absolute percentage error for one step ahead, for multi-step ahead, and then do the visualization for you. And as you can see, previously we were using 2 lags. So with 2 lags, we didn't get the good numbers. It was 10%, 16%. But obviously, if I use more lags, it's going to do a better job, right? So this is how it looks like. Okay. So, and the rest is just, again, in the output of this function, I just want to print out the data frame as well. So to just give you a sense of what we're doing here. Again, you can turn any of them on and off. So for example, you can go ahead and turn off the data, the return data, you can just return nothing, okay? Yeah, then this is me just going over another example. I'm using passenger data, again, using linear regression now, using 12 lags. Yeah, your linear regression is doing a decent job, for one step ahead, multiple step ahead. And then I can go ahead and use random forest. I make sure that the bootstrap is false, at least because we're not doing any kind of time series cross-validation. We want to make sure that the bootstrap that we're doing is correct, especially if you... Yeah, the thing is that we're using 12 lags, right? I think we talked about it in the previous intuition Python video a lot, that why this bootstrap needs to be turned on or off. So I'm using 12 lags, and then with 12 lags, honestly, if I turn it on, it's not going to make a huge difference. It's not going to be wrong, right? But I would be more comfortable if I turn the bootstrap on or turn it true if my dataset is stationary. When it is non-stationary, probably I should keep this false, right? So yeah, this is your random forest. And as I said, we can do... Okay, now... Again, we have a nice function. We can do more pre-processing, right? I can say, for example, instead of applying it to passenger, apply it to something called log passenger, right? Because we want to control this increasing variance, right? So let's take the variance under control and then use log and then just pass the log to this target variable, and the rest is pretty straightforward. So let's go ahead and do that. Yeah, this is the prediction. Okay. All right, and again, I just want to show you that you can apply any kind of Scikit-Learn compatible machine learning model. So here I'm using k nearest neighbors. Again, the default values, you can play around with we can change the number of neighbors to different numbers. Obviously, this is not doing a good job here. And it is expected. When it comes to regression analysis, typically KNN is not going to do a good job. That's why we didn't cover it in the theory lecture. Yeah, that was it. That was pretty much it. The rest of the code, this notebook, is just me going over PyCaret, and you will see that at the end of the day, you're going to do something like this. Let's see this. And this is very close to basically what we did. You pass a name of a model, you create that model, and when you're setting up the environment, you have to say, hey, this is data, and this is your target variable. Now, hopefully you're realizing that how we were able to basically replicate a PyCaret type of model for time series analysis using Scikit-Learn package. Okay, sweet. Let's talk about the PyCaret section and wrap up this notebook. So this is pretty much the same as what we did in the previous lecture videos for Python. We did the same thing for ETS, ARIMA, so I can go ahead and speed up. The only difference is that we changed the model from ETS to, let's say, decision tree. That's it, or random forest. So, but I think we talked about it before. If you're working with PyCaret, you have to specify the periodicity. So here, this is the first thing you need to do. You need to change the index to a date time, and then the period, you have to specify it. Otherwise, the PyCaret is going to complain. So that's the only extra step you need to do. And then from PyCaret time series, import everything, create our first experiment. This is a time series forecaster experiment. And then let's set it up, pass the data frame, session ID. This is just the random number, right? Forecasting horizon 12, and then target variable passenger. So we can go ahead and then train it. Well, not train, we're going to set up the environment. You can do lots of feature engineering or data pre-processing using PyCaret as well. So the documentation is very rich, and then I expect you to just use LLM and read the documentation carefully, and hopefully you're able to deliver whatever you want to do. Okay, cool. And then let's see what models we have. Well, actually, this is compare models, right? I wish I didn't run this, so it's going to take a while. So basically, it's running a horse race between all the models available in PyCaret for time series analysis. That includes both econometrics and machine learning. So by the end of this lecture, by the end of this module in the course, you're able to do and analyze all the econometrics models and machine learning models that are available in PyCaret. But the thing is that, I think we talked about it last in an intuition video as well. When you're doing a machine learning model using PyCaret, just look at this CDS_DT, CDS_DT, cat boost, CDS_. All the machine learning models, they have this CDS_DT attached to that, right? And if you remember, what was it? It was conditionally deseasonalized and detrended. So the way that PyCaret is doing things is that it's going to take this, detrend it, and deseasonalize it, and make a prediction on that thing. And then when it wants to print out the predictions, it's going to bring back the seasonality and trend, right? So the reason that I'm confident with this PyCaret approach is that at least when it's doing random forest and for example the bootstrap is equal to true, it's applying it to a stationary data set, and we're less concerned bootstrapping a time series which is stationary and using, for example, 10 lags or 12 lags. It's not going to be wrong. We're not messing around with the temporal information in the data set, right? The temporal information is reserved in that detrending and deseasonalizing thing. When we add the trend back, add the seasonality back, we get that temporal information. Okay, cool. So yeah, let's see. So these are the models. It seems that for this simple airline passenger data, our exponential smoothing, the ETS model, is the winner with the smallest MAPE, mean absolute percentage error. So you can turn on, I can by default the cross validation is on. So this is cross validated data. These metrics are cross validated. So we can, basically it's this is the best one, the winner, an econometric model, and we are not surprised at all, because we talked about it in very detail that when you have a well-behaved data set like this, if the data is screaming at you, there's a clear trend, there's a clear seasonality. We said do not waste your time with more advanced and sophisticated model like machine learning or deep learning. Why? Because, again, econometric, number one, is very effective in modeling those things. Number two, it doesn't require that many information. So even if you had, let's say, 100 observations instead of 140 or 144, it would have done the same job. Even with 60 observation, it would have done the same job in terms of predictions, okay? But that's not the case for machine learning and deep learning models. So that's something to keep in mind. Yeah, we have our benchmarks. The naive benchmark is not doing a good job. Our grand mean or the grand average is not doing a good job. So this is obvious, right? And so this is the winner, right? The winner is ETS with multiplicative seasonality and additive trend. So this is our ETS model. Then so this is a notebook for machine learning, right? So for machine learning, for example, let's take a random forest. Let's create a model, call it random forest, RF. And we can switch off the cross validation. Again, you can turn it on and off, it really doesn't matter. And now the MAPE is 4.8. So this is close to what we got from this. Remember, we created our own function, ml_ts_forecaster. We passed that, and I think we got 5%, 4 point something there, and here's 4.8. So this is pretty close. So we were able to replicate something like this using PyCaret. Okay, yeah. And yeah, so the cool thing with PyCaret is that you can tune it by using tune model. So I'm tuning this random forest, optimizer MAPE, mean absolute percentage error. So you'll see what is the optimal. Let's see if you're able to improve it. Yeah, we go from 4.8% to 4.5% on average for the cross validation, which is fine. So let's say we're gonna plot that tuned model, random forest model, and forecast into the future. So 12 steps ahead. So this is it. So this is how it's going to look like, right? And obviously I can go more than that. I can forecast 24 steps into the future, right? So yeah, this is where the MAPE is coming from. And then for the rest of it, we don't have, of course, for here, we don't have any metric because there is no actual test set. All right. So hopefully that was helpful. And one last thing I want you to pay very good attention is that either when we were doing Scikit-Learn or PyCaret, there is no confidence interval. So I want you to go back to our previous videos when we were doing econometrics model, right? So when we were doing ETS, ARIMA, whatever, when you use PyCaret, it was able to create that prediction interval or confidence interval for you, 95%, 90%, whatever, right? But for let's say for a machine learning model, as you can see, there is no prediction interval generated by PyCaret. The reason is pretty straightforward. When you're estimating machine learning models, you're not estimating the variance of the errors at the same time. Remember, in ETS and ARIMA, we talked about that sigma, that little thing, sigma thing. We said that because there's a closed form solution, we can go ahead and find, for example, a closed form solution for the formula for sigma, and we can use that one to come up with the prediction intervals, right? For machine learning, that's not the case. Your models are non-parametric, right? So for example, this random forest is a non-parametric. At no point we get a luxury to estimate that sigma, the variance of the errors, right? So because of that, we cannot use that. So how can we come up with a prediction intervals for a machine learning model or for a deep learning model? This is a separate topic that I will cover it in some module called miscellaneous. And I will talk about, for example, how we can use Bootstrap to come up with prediction intervals, how we can use, for example, quantile regression to come up with the prediction intervals, or most importantly, how we can use something called conformal prediction to come up with prediction intervals. So conformal prediction is something which is becoming so popular, and actually it's valid. We're going to talk about all these things later on, but that's by the end of the semester, by the end of the course, right? Once we're done with all the machine learning models, deep learning models, and econometric models, and we can talk about the point forecast, so these are the point forecasts, then there's at the very last module, I will add this something called miscellaneous folder, and there you can see how you can use, for example, conformal prediction to come up with a confidence interval for a machine learning model. If you want to see where you can find it, so go to the GitHub account. Let me actually show it to you. If you go to the GitHub folder, lectures and codes, as you can see, I have added a miscellaneous folder. If you go there, there's a prediction interval. So if you click on this, basically this is a code that show you how you can add prediction intervals for a machine learning time series, right? We can apply the same thing to a deep forecasting model as well. So I'm not going to do a video on this one, but just for those of you who are interested, you can go ahead and read. This is pretty straightforward. You can read through this notebook, and hopefully you get a sense that how we can do confidence intervals using machine learning model, right? So again, there are bootstrap methods, and there are, let's say, quantile regression, which applies to a linear model. So this is we come up with this, right? Quantile regression, the downside of quantile regression is that your model needs to be linear, so we can apply it to a simple linear model. So this is the confidence intervals for quantile regression. And then finally, again, this is the most exciting one, which is conformal prediction. I might do a separate video on the theory of conformal prediction. For time series, it's not that complicated. So hopefully if you read this, it's straightforward. But if not, again, I'll try to do a lecture video on that one as well. But you need to install another separate Python package called MAPI, or sometimes people call it MAPI. But this is MAPI, it stands for Model Agnostic Prediction Interval Estimator. And the cool thing is that this method is model agnostic. So you can use any model. As long as you have the prediction, you can come up with confidence intervals, or they call it conformal prediction. Okay, and this is how the conformal prediction looks like. Okay, so I want to stop this video because this is lengthy enough, but just for those of you who are curious why we did not talk about conformal confidence intervals for a machine learning model, simply because we didn't get a chance to estimate that sigma. So we cannot, because this is a non-parametric model, we cannot come up with a closed form solution for those variances. So that's why we have to use the other numerical methods like bootstrap, quantile regression, or conformal prediction. All right, that was pretty much it. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.